Swayam Prabha. Digital India. Educated India.
Okay, so next we are going to look into something called okay, the first thing is so I'm sure like all of might you already heard Gaussian random variable, right, many times. So let's formally define that. Gaussian distribution, we are going to denote it as with the symbol mu sigma square, where mu and sigma square are the parameters. Like earlier we had Pn as the parameter. For the Gaussian distribution, mu and sigma square are the parameters, and here mu is a real number and sigma square is a positive quantity, and it could be also take 0 value. Now this is, we are talking about continuous random variable, right? So we are now going to define the probability density function of this random variable. For a Gaussian random variable, we are going to define its density as of x and this is provided my sigma square is strictly greater than 0, and if it is sigma square equals to 0, then it takes a degenerative format. In that case, it is simply going to be of this form 1 if x is mu. So this is if sigma square greater than 0, otherwise we are going to, it takes a degenerative form where it will have only one possible value at x equals to mu and 0 otherwise. And its characteristic function is given by function exp So it so happens that for this Gaussian random variables with parameters mu and sigma, the mean turns out to be the parameter mu and the variance turns out to be the parameter sigma square. So we are just going to call a random variable Gaussian with the mean something and variance something. So the mean is nothing but that parameter mu and sigma square is the other parameter. Okay, so here if you look into this, this is a PDF and this function is valid for all r. As for for all r, for all x belongs to r, and now let me know, if sigma square is not equals to 0, then my CDF is going to be defined like this for all x, If not, sigma square is 0, then it has this format and its characters functions are given like this. So let's just, because this is one of the most popular distributions that is used, let's see. So let's say this is my mu here, and this is my x, and this is my x. So just looking at this function here in variable x, is this function symmetric in x? About what? About mu. Just by looking at this, you can see that because this is a square term here, it will be symmetric about x. So whatever and it goes on like it is defined for. It does not look symmetric, but fine, it is symmetric. And suppose let's say this is for some sigma square and mu. So suppose I increase this variance sigma square, how do you think this lobe will look like? I will keep the mean same. Suppose I want to have another random variable, Gaussian random variable with the same mu, but let's say it has a variance which is larger than this. It will decrease. It is going to be this lobe, it become fatter, right? Like and it will like maybe like something like this. Maybe this sigma 2 square is going to be larger than that. But now if you have some sigma 3 which is going to be smaller than sigma 1, how it is going to be? So in this case it could be like it is going to get thinner. And eventually if you are trying to make it sigma square to be 0, it will be just this, a delta at x equals to mu, this is going to just take the value of 1 and it is going to be 0. Okay. Yeah, so if it is sigma square equals 0, this height is just going to be 1. That is the only point where it will have positive mass and 0 everywhere. Fine. So I have a Gaussian distribution like this. Where you want to use it? You know it's very popular, right? Where it is used or where you think it's going to be of natural use. Or you feel that I can't imagine anything where this can be used. Huh? IQ distribution of humans, animals, humans, okay. So what is the range of IQ? But range क्या है? 0 होता है क्या नेगेटिव होता है? 0 मैक्सिमम कुछ भी? Is there an upper bound on IQ? Or somebody can have infinite IQ? Theoretically infinite. But then one side is fine, right? Like negative तो नहीं हो रहा है. So 0 to infinity. So this one is, by the way I have defined, it has also negative values here. Right? So if you have only positive values, maybe you don't want to use it, right? What could be other example? Yeah? Yeah, but again if you want to begin with, you know that the height is going to be some in the range let's say some 2 feet to 6 or 8 feet, and it is never going to take a negative value, right? But still, yeah.
So we can cut it off on that side and then scale the function, right?
You want to cut it off and
Cut it off on that side and then scale it by integral from 0 to 1.
yeah, you can condition,
Can be
but before conditioning I'm talking about. Yeah,
a game of gambling
yeah,
where X is going to take a total profit or loss by the end of some particular.
yeah, fine. So maybe that is one possible thing. Like let's say you are like a big angel investor, maybe you can make billion dollars, or if your investment goes dish, like you may make negative $1 billion, and so you have a big range, right? Maybe
Its other application is in that tolerance design for the companies.
tolerance design. Okay, so yeah, can you make this more concrete example?
So suppose we are manufacturing nuts and bolts.
Hmm.
For that we have set up the mean value to be something. Suppose let's take 50 microns.
Hmm.
So we just don't want to increase that tolerance. We are taking that to be 0.1 or point specifying it to be so that there is not the manufacturing defect or something like that.
Okay. So another example I can think of is like let's say some kind of deformation with temperature, right? Like I can apply temperature can be both positive and negative, right? In some critical applications, temperature can have a wide swing. So if you are going to apply this positive temperature, how your deformation or whatever the related quantities look like, and when the temperature goes below negative, how it looks like. So there are again like it is just about that, as you can see that it finds many application, but it has this need to have both positive and negative value, but that's not a constraint. Like you can always you can adjust about your mean and take care and so as long as you feel that there is something heavy concentration about a particular value and then things slowly die down around it, maybe this is a good thing. Even in case of a population or a height distribution, like height, let's say this is like about 5 feet, there is maximum number of people around 5 feet, right? Most of them, like then other guys maybe like just die down. Maybe if I go here itself like around 5.5, and if I just take it like maybe 4.5 here, already significant reduction is happening. So this is in that way, at least in this region, it is still like looking more like a Gaussian distributions, right? You can still continue to use that, but provided that you appropriately. So you, I mean, right away when the Gaussian should come to your mind whenever you see that there is something like there is something going to be symmetric around some value, and there is going to be like as I said diffusion or dispersion about it both on the left and right hand side. Then you will do so. Okay, fine. You may feel that okay, this is a good, but I don't know how concentrated this lobe should be. This should be thin or it should be big. That you find it from your data. You do a lot of experiments and see that how you going to fit your data so that you get the right parameters mu and sigma square. So fine. So this is one thing. Now we are going to see another distribution called exponential. And the PDF of this distribution, we are going to take it as f of x equals to lambda times e to the power lambda x, and this is going to be for all x positive, and its a characteristic function So this distribution is going to look like, if you give me lambda, so this is going to start at x equals to 0, this is going to be what, simply somewhere it is going to start from lambda, and where it is going to go, it is going to go to 0 as x increases. This is my f of x. Suppose in this I increase my lambda, let us say this is for some lambda, and if I increase my lambda here, what do you think, how this another function is going to look like? So at least I know that if I am going to increase, so let us say this is for some lambda 1, and let us take a lambda 2 which is bigger than this lambda 1. At least I know this starting point was lambda 1, the other point is going to be lambda 2. It is going to fall much faster, right, because this is coming in the exponential term. So maybe it will start faster, but it will decay much faster. Okay, fine. So I have such a probability density function which is taking positive values, I mean which is defined on positive real half. So where you think such a, and you see that as x increases, this is going to like fall rapidly, it is falling actually exponentially fast. So where do you think such a distributions can be helpful? What kind of things you would like this to be used to model? For example, let us say some component in machine, what machine, like component what? Let us say I have a component, I want to predict the lifetime of this machine. Like fine, let us say I have a bulb and I want to see how long this bulb is going to survive before it breaks up. So it may last, let us say its count, let us say let us count a life in terms of second, it may last 100 seconds, 200 seconds, or maybe 1000 seconds, and maybe like 36,000 seconds or whatever, like after that it may break, right. So you feel, as you see that if you are expecting it to survive longer and longer, that probability is going to be falling rapidly, right. So that is what in that case maybe this kind of exponential distribution is going to be much useful. And in that case, if you have two, let us say bulbs, one is of a better quality than the other, and so which one you want to assign higher value of lambda, the better one or the poorer one? Poorer one, right, because with that it is going to decay much faster. So another good thing about this exponential distribution is it has the memoryless property we already discussed. So we discussed memoryless property with respect to which distribution? Geometric distribution. Geometric was a discrete distribution. So it so happens that this is a continuous distribution, but it also satisfies that memoryless property. What does that mean? What does that mean? Suppose you have your random variable x is going to take value larger than x plus t, given that it has already taken value larger than t. If x is memoryless, what do you expect this quantity to be? You expect this to be just probability that greater than or equals to s. So do please verify that if you have CDF like this, it is indeed like if x has a CDF like this satisfies this property. Okay. Okay. Next is uniform. uniform, I'm going to denote it by B, where my and the PDF of this is for all A between and B, and I'm going to 0 otherwise. And its characteristic function is given by e to the power j u b minus j u a by j u minus b minus a. And again its mean is going to be, you can work out that its mean is going to be simply the average of the points A and B, and its variance is B minus A whole square by 12. So what it is saying is, like, suppose if I have a, let's say I want to assign, let's say I am interested in some interval A and B. I want to say that anything in this is equally possible. Okay, that means what it is saying, that for all x in this range, all of them are going to take the same value. So that is this, the function u here is going to be simply this quantity, where this quantity here is 1 upon b minus a. So this PDF is like a flat in the interval A and B. That means if you interpret in terms of the intensity, at every point the intensity is kind of the same here, and anything outside we are not assigning any probability. So you can just see that the mean of this is going to be simply the average of these 2 points, and the variance you can compute like this. So where do you want to use such a distribution? Like say let's say in terms of the temperature, right, like often, like what did you, we can say that the temperature of a day may be like uniformly distributed in so not necessarily like a temperature, let's say anything you want to apply, like let's say pressure on something, the amount of the pressure that this guy can sustain could be any uniformly distributed between the two extremes. Let's say some minimum amount of pressure and some maximum amount of pressure, it could be taking equally, like it can break at any of this amount of pressure equally likely. So this is one possibility. Other anything other useful things you can think of? Like maybe like fine, you have grades like A, B, C, D. These are discrete, but think of instead of this, think of these are numbers between 1 to 10. I can think of like the distributions could be uniformly, like the distribution of the marks could be uniformly in between 1 and 10. Can I use that? Yes, good. So you want to be uniformly distributed, the marks between 1 and 10. Okay, fine. That's and then comma. And then in alpha real and real. So the PDF of this so actually when you have this Bernoulli toss, right, we have only head and tail. Suppose you assume it's a fair coin, that is taking head is half and also tail is half. So then we can say that both my outcomes are equally likely, right, or my head and tails are like uniformly distributed. That is in the discrete version. So what we are now talking about is uniform distribution in the continuous domain where any value in this interval is like equally likely. Okay. So PDF is alpha to the power n. And you can find that its characteristic function is its mean happens to be n and so another useful distribution is gamma distribution. So it has again defined on for n integer and for any x which is non-negative valued. Gamma n, this is a gamma function where gamma is defined like this. Okay. So what is the usefulness of this function? So it so happens that gamma function is related to exponential distribution. In what manner? If you are going to take gamma to be n alpha, this is related to exponential distribution through it so happens that this distribution can be expressed as sum of n exponential distribution with parameter alpha. So if you are going to take this gamma to be alpha and add such n exponential distribution, then you will end up with gamma distribution. It needs another requirement that these are independent. Further we will define what we mean by independent today later in the class. So if we add n independent exponential distributions with parameter gamma, then we will end up a distribution which is gamma n alpha. Okay. Last one is its PDF is so its characteristic function is a bit complicated, I am not expressing here. Okay, so what is this Rayleigh distribution? So this Rayleigh distribution, I think I am not going to use this much, but this may be useful to this communication network people. It so happens that it comes very handy when you have to deal with multiple Gaussian distributions. It so happens that this gamma Rayleigh distribution with parameter sigma square is nothing but the envelope of okay, so it is going to be so first let me explain this. So if x and y happens to be Gaussian distributed with parameter mu and sigma square where mu is set to 0. the sigma square is going to be same as this sigma square. So then it so happens that the distribution of this turns out to be this Rayleigh distribution. So okay, suppose you are dealing with let us say two quantities, random variable x and random variable y, which are both Gaussian, independent, mean 0, variance sigma square, and if you need to happen to deal with such a quantity, so instead of looking at each of them separately, you need to end up with, so this is like what? This is x square plus y square will give what to you? Kind of circle, right? And you want to take a square of that, and you want to understand this is kind of a radius of this circle, right? You want to understand if at all it has a constant radius. This radius could be varying. You want to understand how that radius is distributed. It so happens that that is can be characterized as Rayleigh distribution. Okay, so it so happens that it can be thought of as instantaneous value of envelope of a zero mean narrowband noise. Fine. So, okay, now just quickly coming back to this uniform distributions. So, uniform distributions, when it is going to be useful, uniform distribution you want to use when among the possibilities you do not have any prior information. For example, let us say tomorrow Mumbai's temperature is going to be between 20 to 30 degrees Celsius, but I do not have any prior information like what it is going to be like. Let us forget, I do not have any, I just born today and I have to choose what is going to be the temperature tomorrow, and I was told that it will be something between 20 to 30. So if I do not have any prior information, what I am going to do is I am going to think that everything is equally possible. I do not have any prior information, right? In that case, when you have to deal with a situation when you have to model some randomness about which you do not have any prior information, you would go with uniform distributions. For example, in this case, exponential, like when I take a lifetime of a bulb, I know that as time progresses, the probability that the bulb will break down is going to increase, right? But in such case, like suppose I do not have any such information. Like let us say I have a bulb and I do not know, like it can break down any time within a 0 to let us say 100 seconds. If that is the case, then I would go and like to model it as a uniform distribution. Okay, if I do not have any prior information, maybe that uniform distribution comes very handy to us.